Yeah, it's your boy Chili here. Welcome back to Shared Memory. In the last video, we got our first test set up and everything working with boost.interprocess. So we're writing a string from one process, we're reading it from another. Everything's working fine. Only one little problem here. I wonder if any of you guys caught this. Yeah, there's a little bug in this line of code here. Can you find it? Well, when we iterate over a range of characters, it only goes through the actual characters. It doesn't do the null delimiter, which is usually what you want. You only want to deal with the actual data. Except in this case, we need to write the null terminator because it's a C string sitting in memory. It needs to know where it ends. So, my bad. Now, we could just use the string copy, but I refuse to admit defeat. So I'm going to do my copy as usual, and then at the end here, I'm going to go p bytes at str.size. So this will be the index of the null terminator is equal to, I mean, we could just do 0, but let's do it fancy. Null character. There you go. Now, what do we want to do in this video? Well, I got two things on my plate. The first thing is I want to reproduce the test that we had in our original shared memory here, where one process is writing values, integers, and updating and indexing here, and then the other one is reading it. So this is happening over time, over a period, every 10 milliseconds, and I want to kind of capture that in a test. So we're going to have some timing involved in our test here. And then at the end of the video, I'm going to drop a little bombshell on you. I'm going to hit you with the central problem of shared memory. And that is going to kind of drive any future videos I make on this topic. So we'll create a new test, timed. Okay, so what's the interface going to look like? Well, what we're going to do is we're going to mostly just mimic what we have in here. So let's put a struct. So we'll share this in our header. Okay, so now we need the interface for the server. So there's a couple ways we could do this. We could just put the sequence buffer here at the beginning of the name shared memory. And so it would basically just overlaying both the string and these ones. You can't have both at the same time. You got to make sure you initialize the correct one. But the other way we could do it is we could just give them separate spaces in memory. But then we have to really give this string a defined length. So we're going to say, hey, the sequence buffer starts at byte 1024. And that means that our string has to be 1023 long, 1024 if you add in the null terminator. So let's just change our interface here a little bit. We're only going to copy the first 1023 bytes. Everything after that is going to be truncated. Let's do auto. Let's do const auto truncated string is equal to string view take sequence buffer offset -1. So that'll take 1023 characters. We use our truncated string to copy, and then we use our truncated string, get the size of that, to figure out where we got to put our null terminator. Now, whenever you refactor your code like this, it's a very smart idea to run your test to make sure you didn't break anything. And it does work as expected, so it's probably okay, isn't it? So we need another interface function here, virtual void write sequence value. Then in here, we're going to do read sequence value. Now we have our interface here, write sequence and read sequence. So what are we going to do? Well, first thing, in the server, we want to initialize. So we're going to actually need a constructor now. All right, so in the constructor, we want to do a placement new on the memory in there. So we do new, and then we got to put the address to do the placement new into, and that is going to be region.get address plus sequence buffer offset. And then we're going to do sequence buffer. And we're going to construct that with a 0 for last written. We could do -1 to show that nothing has been written yet. Maybe that's better. One little problem here is you can't, do pointer arithmetic on a void pointer. So we need to cast it to car first. This kind of brings to mind, maybe I'd like a few little helper functions here and there. So create a little helper function here to get the address at the beginning of the shared memory mapped region as a car pointer. And then I'm going to construct a new sequence buffer in the shared memory offset by the sequence buffer offset. We're gonna initialize the last written, I forget what the member is, last written to -1 to show that it hasn't been written to yet. Okay, so this has the sequence buffer. I'm also caching the pointer in this member variable here just because I can. Now we need to implement the interface, which is write sequence value. Auto I is equal to p sequence buffer pointer to last written. Start off as -1. Then we can do I plus and equals 1. Increment that. So we'll do if plus I is greater than std size p sequence buffer pointer to last written. The buffer, the buffer. So this should give me the size of the buffer, which, yeah, 1024. Then I is equal to 0. We roll it back over to 0. Then once we have the index to write to next, buffer at index is equal to value. And finally, we want to update the last written. What is your problem? We got a missing brace there. So that's p sequence buffer pointer to last written is equal to I. So we write, and then finally we update last written. So on the client side, I'm going to change things a little bit. I am going to read sequence value is going to return optional int. Basically, it's going to work like a circular queue. And so as long as you don't wrap around, it will work properly. You'll read up until there are no values left to read. You've read them all. So if there's nothing left to read, it'll return an empty optional int get last written. So this will be able to tell us whether it's been updated if we're waiting on an update, which is what the test is going to do. We're going to need a little bit of data. When we initialize, let's just cache a convenient pointer to ya boy. P sequence buffer here, so we'll need a constructor. Note I also added in the bytes helper in here. When we offset into the bytes, we interpret that as a sequence buffer pointer and store that. Now we also want to store the last place that we read. So int last read is equal to, and we'll do -1 initially for not having read anything. So read sequence value, what it's going to do is if last read is not equal to, so we read last written, we check to see if last read is different than that. If so, we try to increment last read to the next thing, because last written could be many past last read. So we just want to get the next one that we haven't read yet. Actually, this is a little mistake here. We should increment last read and roll it around, and then we should return p sequence buffer at last read. Now, if they are the same, if last read is equal to last written, we don't do anything, we just return an empty optional. There was nothing there to consume. And get last written sequence value is very simple. Just return whatever is in the structure. All right, so this should be the interface now for the new test. So we're gonna have a new shim test case, shared memory test case, and it's gonna be timed sequence producer consumer. We're gonna include chrono. I don't want to do sleep because sleep isn't that accurate. So I want to be fairly accurate with my timing here. So we have a little lambda that is going to allow us to spin wait, takes in a duration, and it will wait until that duration has elapsed. So we create the server. We're going to tell our partner to go ahead and connect to the server. And when we get an ACK back from our partner, we are going to begin the process of spitting out numbers. The input in the code string is going to give us the stride and how much we want to increment our initial value. For views iota, so we're going to start at 0 and we're going to be incrementing by stride. And let's define that this test should only run for 7 iterations. For int x in this range, we're going to spin wait 3 milliseconds. Then we're going to do p server write sequence value x. So this test should run approximately 7 times 3, so 21 milliseconds plus whatever overhead, so around 30 milliseconds, I guess. Then after this, we're going to wait for acknowledgement from the client again before we exit. So let's copy this test to make a new test on the test framework side here. Connecting is the same, shared memory test, but we want to change this to timed sequence producer consumer. We want to change the test name to match this one. Now the code string is going to be the stride that we want to use. And let's use a stride of 25. So we read the go-ahead, we connect the client, and then we acknowledge that we've connected. And now what we want to do is read the sequence 7 times. So for int x in views iota 0.5, 0.25 takes 7. So what we're going to do here is we are going to capture start time. Then we're going to spin wait for a new value. Actually, instead of get last written sequence value, it might be better just to do like has sequence value or has new value. Has new sequence value bool. And we'll just return last read is not equal to last written. I think this is better for our purposes. So while we don't have a new sequence value, we're just going to spin here. Then we're going to do const auto end is equal to, and then we should assert r equal, expected is x, and actual thing is p client pointer to read sequence value. And we'll just assume that we can get it because of the fact that here we have new sequence value. There's a bit of a race condition involved in here, but it's fine in terms of the time scales of these operations. But I mean, like theoretically, it's possible for the server to write 2 values, but we're only expecting it to get 1 new value at a time. Now, that's not 100% guaranteed, but it's like 99.999999% guaranteed, so that's good enough for me here. First thing I want to assert is that sequence value matches the one that we expect. The second thing that I want to end minus start should be greater than or equal to 3 milliseconds, because that's the time that we waited on the server. So it shouldn't be any less than that. Now there's another thing that we could possibly do in here, which is if something goes wrong and the server never writes, we could just be blocked in here and the test will just stall. It'll just keep spinning and it'll ruin your whole test suite. So what we can do in here is do a little timeout test. We're timing it for 3 milliseconds. It shouldn't take any more than 4, but we'll give it a little more leeway than that. If start minus now is greater than 10 milliseconds, if we've waited longer than 10 milliseconds without getting an expected value, then we want to assert fail with the message timeout. All right, and so here we should read the 7 expected values. We should out, not cout, just out, and ac. If I'm being honest with you, I don't really have much confidence that's going to work on the first try. We declared an existing local variable because I copy and pasted. All right, moment of truth. I doubt this is going to work. Yeah, it didn't work. Assert failed. Line 154. So let us give ourselves a little bit of, let's do const auto duration is equal to end minus start. And then we can put the duration in here. Logger, write message. Std format, duration. So hopefully std format handles std chrono, and I think it does. Now let's just put some text in here to make it a little nicer. All right, let's run this again. Assert failed sequence duration shorter than expected. And it is, that looks like 3 milliseconds, right? Because that's microseconds, nanoseconds, and milliseconds. So duration for number 0, 3, which is right. Number 1, so the one right after it is the one where we get kicked in the nuts. Now this could be because of time spent doing the assertions, writing the message. Like during that time, the server might have already written another value. Or it could be because we're not updating something properly. And now that I think about it, I think it's the other one, and something is starting to scratch in my brain here. So first things first, give me a \n there. Run it back. Here we go. Duration for 0, 3 milliseconds, almost on the button. And duration for number 1 is 1 microsecond. Okay. Read sequence value, go to definition, is not updating last read. No, wait a minute. We do ++ last read here. This is not a local variable. This is a member. So it shouldn't be this. So the other options are this shit is taking too long. These asserts and the logging. I know that std chrono high resolution talk doesn't take that long. So that's one option. The other option is the partner is writing too fast. So the spin weight is broken or something. We could try something. We could try not putting this assert in, running it again. Just seeing what we get. It's very interesting. It's like this one, a lot shorter. So I don't know why it stabilizes down here. I know why it's a little less than 3 milliseconds is because of probably, you know, the work done in here and here. We'll get rid of this logging. The logging could be causing an issue, but 3 milliseconds is a little too tight. So let's bring it down. So 2.5 milliseconds. This is the thing I was talking about with like the race condition, although not exactly what I had in mind, but it's still similar. It's a very kind of loosey-goosey kind of test. Now it works. So I think the problem with those really short ones was caused by logging. The logging was messing with the timing. And the initial problem why it didn't work is because 3 milliseconds is too tight. These asserts take a little time. So I should bring it to like 2.5 milliseconds. Give the producer a little leeway. So there we go. But this is working, and let's run it a few times to make sure that it's not completely brittle. It's not like the best test because it is dependent on some timing stuff. But with this much leeway, with 500 microseconds leeway, it shouldn't be a big deal. Yeah, now it's running fine. So there you got like a fairly complicated sequence time test for IPC. It was interesting. Pulled on a bunch of different tools in our toolbox there, in our C++ toolbox. Now I'm gonna hit you with a little bit of a tricky one here. Throw a little conundrum to you. We're gonna add to our shared memory a pointer to a string. And it's gonna be a pointer to the string that's at the very beginning of the shared memory. Just put a pointer in there and then try to access it from the client, right? So that is going to be the sequence buffer offset plus size of sequence buffer. So this is the offset to a string pointer. So make a little function in the client interface to get string pointer. There's actually one little thing that I just came to mind that I should probably have done. I should make this sequence buffer in the client. This should be const volatile. Just for funsies, I'm going to run the tests again to make sure that that didn't break anything, but it shouldn't. It should make it better. But yeah, if you're looking at like memory that could be changed by like another process, it should probably be listed as volatile so that the compiler doesn't do any weird optimizations that stop it from reading the actual memory. It says, you didn't change it since the last time I read it. I'll just use the cached value, and that does not work well. Okay. So anyways, get string pointer. New bytes underscore plus string pointer offset. Create a car pointer in that memory initialized with the address of the string, which is just bytes. So we create that pointer in there. Now then in the client, we want a way of reading that string pointer. So again, we get string pointer const override. And we're just going to return. So I'm going to reinterpret cast. And then we dereference that pointer to a car pointer to get the value of the pointer that is stored in the shared memory. So this gets us the pointer that is stored, the address basically, the address that that pointer is pointing to. And so what we should do, we shouldn't even need to add a new test method here. So we could use the same test case on the companion process. Pointer read from server, but this one's going to use basic read from server. We can use the same stuff here. Change the string a little bit just to mix it up. Now instead of doing read string, I'm going to do std string read is equal to pclient get string pointer. So we're going to create a string based on this pointer, and that is what we are going to compare to expected. There you go. Build it. All right, let's run our tests. Does not work, and it throws an exception. So it throws an exception right around here when we are initializing our string, trying to read from this pointer. So there's something wrong with this pointer we're getting here. Is not kosher. And my question to you, my little conundrum, for those of you in the comments, where's the problem? You know, we write a pointer to the string, just a pointer to the beginning of the same pointer that we've been using to access everything. We're just writing that pointer into the shared memory on the server side. And then on the client side, all we're doing is reading that pointer, then trying to access that string via the pointer that we had put in the shared memory. And it doesn't work. It does not work. So why? Why doesn't it work? You tell me. Tell me why this doesn't work. And that's going to be the topic of the next video. Well, until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button, helps a lot. And I'll see you again with some more shared memory in C++.